Hi, it's Kate, and this is the second video for week 12 of Math 23. So we talked a little bit about the implicit function theorem, and now we're going to talk about where and when we can use it. And most of the time, in this course at least, and also in your other courses, physics and economics or whatever you may be doing, maybe computer science, you will probably be working with manifolds when you're dealing with the implicit function theorem. And the first question on everyone's mind is always, what is a manifold? So a manifold is a generalization of smooth curves and surfaces. Basically, they're a family of particularly well-behaved smooth functions that allow us to apply all these different theorems to them. So let's talk about the really most basic type. Well, the simplest sort of manifold is a flat one. It's just described by linear equations. So an example is a line that has a particular slope. In this case, we're given slope 2 that passes through 0, -2. That's a one-dimensional submanifold of R2. There are some other ways to describe manifolds, not just writing, this is a line of slope 2. Well, the first one is that it's the graph of a function that expresses the passive variables in terms of the active variables. And what's going to blow your mind, or at least did when I was a student, is that a graph is not a picture. A graph is not a picture. A graph is a set of points that obey a particular relationship. And so when it says draw the graph, that's why you end up drawing that picture. Those are the set of points that obey a particular relationship, y equals blah, 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 blah. But I guess popular conversation has sort of taken the word graph and turned it into being synonymous with sketch or drawing or picture, and it's not. A graph is the set of points that obey a particular relationship. So our very first definition of a manifold, which is technically, the normal definition, is that it's the graph of a function that expresses the passive variables in terms of the active variables. Here is a graph. Y equals -2 plus 2x. That's the set of all points that lie on that line of slope 2 through the point 0, -2. Alternatively, you could pick that x is the passive variable that's described in terms of y. So x would be equal to 1/2 times y plus 2 quantity. It's a little bit of jargon that we just need to get used to using in the right way. So this is the first way of describing a manifold, that you say passive variables equal, and then all these functions that just involve the active variables. The second way is that you could describe a manifold using a locus, which is a constraint equation. It uses both the passives and the actives and basically puts everything on one side of the equation so that the other side is 0. Locus functions are always set equal to 0. So in our particular case, we have that y equals -2 plus 2x, just like shove everything onto the other side. So we have 2x minus y minus 2 equals 0. And the very last thing is a parameterization. And a parameterization is a way to describe all the points in the graph using a parameter t. So in this particular case, our parameterization is the point 1, 0, plus all the possible scalar multiples of 1, 2. The vector. So that point 1, 0 sort of puts us on the line, and then all these possible scalar multiples of the vector 1, 2 slide us as far out to the right or to the left of that point. So let's take a look at the definition of a smooth manifold. So a subset M being a subset of Rn, is a smooth manifold if locally it is the graph of a C1 function. Well, a C1 function means that its partial derivatives are continuous. Locally means that for any point in the set M, we can find a neighborhood U, which is an open ball around X, such that within the intersection between that neighborhood and the manifold, there is this nice C1 function that expresses the passive variables in terms of the active variables. That's all that means. So again, it's a smooth manifold if locally it is the graph of a C1 function, which means that I can pick any point on the manifold, and in a open ball around that point, there exists some function that takes those passive variables and expresses them in terms of the active variables. The number k is the dimension of the manifold. It's the number of active variables. And in R3, there are 4 possibilities. One is where you have a 3-dimensional manifold. So any open subset is itself, in R3, is itself a smooth 3-dimensional manifold. The manifold is the graph of the function f, which maps R3 to the 0 vector, whose codomain is the trivial vector space 0, and that just contains a single point. And that function is necessarily constant, right? It maps always to the same point. Its derivative is going to be 0 too. Let's take a look at some other examples. Well, say we wanted a 2-dimensional manifold in R3. Here's an example. The graph of z equals x squared plus y squared. It's a paraboloid. I will draw one for you now. There you go, my beautiful artwork. You know, 1-dimensional manifold in R3. Here it is, where we describe it in terms of z, where x is cosine 2 pi z, y is sine 2 pi z, and that is going to be a helix. Sorry, that drawing was not nearly as impressive as I had hoped it would be. And a 0-dimensional manifold. In this case, the manifold consists of 1 or more isolated points. Near any of those points, it's the graph of a function that maps from the 0 vector to R3. Domain is the 0-dimensional vector space, whose image is a point x naught in R3. It's the point that we chose back here. This function is differentiable because since its domain only contains 1 point, you cannot find nearby points to show that it is not differentiable. Haha. But there's no requirement really that a manifold be a graph of a single function or that the active variables always be active at every single point. You can actually, on a manifold, the function that describes the manifold can change from sort of part of the manifold to another part of the manifold. Maybe another function describes it a little bit better on another side. And this is actually true of the unit circle. So the unit circle is the locus of x squared plus y squared minus 1 equals 0. That's the second way we describe manifolds. And when you take a look at it, it's actually going to be a union of 4 function graphs, 2 of which have x as the active variable and y is passive, and then the other 2 have y as the passive variable and x is the active variable. And I just realized I said the same thing twice, so scratch that. 2 of the function graphs have x active, y passive. 2 of the function graphs have y active, x passive. There we go. Thank you. Okay. Alternatively, we can use a parameter t that is not one of the variables and represent this by the parameterization x equals cosine t, y equals sine t, because that is the unit circle and that's how we define all the points on the unit circle. Let's take a look at actually putting the implicit function theorem to work on a manifold. All right. What do we have here? Well, we have this open subset U of Rn. We have a C1 function, continuous partial derivatives, of a function f, that's the function, our C1 function, that maps from this open subset to Rn minus k. We consider the locus, which is in the intersection between M, the manifold, and U, the open subset. The locus is the set of solutions of the equation f of z equals 0, right? F of anything equals 0. That's the constraint. That's what's telling you this is the relationship of the points on this manifold. If you're on the manifold, then the locus equals 0. If df of z is onto, surjective, for every z in this intersection between U, the open subset of Rn, and M, the manifold, then this little slice of heaven here that's in the intersection between the manifold and U is a smooth k-dimensional manifold embedded in Rn. And so what we're trying to do is sort of at each point on this larger manifold prove that all of its pieces are also manifolds. So we just need to show that sort of all the pieces are smooth and well behaved in the way that we want them to be for this whole thing to be classified as a manifold. The implicit function theorem actually says precisely this. The statement that df if z is onto guarantees that the implicitly defined function will be differentiable. And if df does not exist or fails to be onto even like at just a single point, then this locus function, which is equal to 0, is not a manifold. And we use the manifold intersected with U because f, right, the locus function may define just a subsection, just as I said before, of like a larger manifold, like part of the sphere or part of the unit circle. And it cannot be described as the locus, like the whole manifold can't be described as the locus of a single function. So to say that M itself is a manifold, we have to find an appropriate open set U and an appropriate F for every single point on the manifold. And that's usually not as hard as it sounds. Well, when we want to parameterize a manifold, let's take a look here. We have a k-dimensional submanifold of Rn. The parameterization function is always notated in our notes as gamma. It's going to map from the open set U onto M. So when you plug in a value for the parameterization, it will give you back a point that's on the manifold. Pardon me, plug in a value for a parameter. It will give you back a point that's on the manifold. Just like with the unit circle, cosine t, sine t, pick a value for t, it'll put you on a point on the unit circle. The variables in Rk are called parameters. Remember that k is the number of active variables. Remember that? So what we're saying is that is how many parameters you should have in your parameterization. The parameterization function gamma must be C1, 1-to-1, and onto the manifold. So in other words, we want gamma to give us the entire manifold. We don't want to be able to plug in multiple points, multiple values for parameters and have it map to the same point on the manifold. We also don't want to miss any points when we plug in all the possible values for the parameters. We say that, the unit circle has the parameterization cosine t, sine t. And t goes from 0 to 2 pi. And that will travel the whole circle. That's a very well-behaved parameterization. These are continuous functions. We also know that if we plug in 0 to 2 pi, we're going to hit every single point on the unit circle. We also know it's 1-to-1. So by going from 0 to 2 pi, if we go any further than 2 pi, we're going to start repeating points on the circle, and we don't want that. So finding a local parameterization that gives part of the manifold is of no particular interest because there is, by definition, a function graph that does that. What's great about parameterizations is that whereas with this unit circle, we actually had to cut it up into like a million little pieces to be able to describe it as a function graph. Like there's one function graph over here and one function graph over here and one function graph up here and one function graph up here. Scratch that. We can throw that out and say, hey, I want to use a parameterization. And that parameterization, we just need one of them, can actually just define the entire manifold. And an additional requirement, the derivative of the parameterization function needs to be 1-to-1 for all the parameter values. And this requirement makes it so that the columns of the Jacobian matrix d gamma are linearly independent. And let's talk about why that actually matters. Segue. Okay, we're now talking about the tangent space as a graph, kernel, or image. So when we look at a manifold like the unit circle and we say like, hey, there's this point here, what is the tangent space there? Well, it's going to be like the tangent line that touches, that's horrible, it didn't even go through that point, but that touches on that particular point. Now, if we had like the unit sphere or something like that, and we wanted a tangent space at this point, that actually ends up being a plane. That's also horrible, but you can kind of envision that plane, it's like holding a loose leaf piece of paper onto a globe. So let's talk about how, depending on how you've described the manifold, how can you figure out what the tangent space is? Scroll down. All right, well, our first option is that we have used a graph of a function to describe the manifold. Well, the derivative of G, which is just dGB, is an n minus k by k matrix. Because remember, G maps from k to n minus k. So dG is going to be an n minus k by k matrix that converts a vector of increments to the k active variables. Y dot into a vector of increments to the n minus k passive variables x dot, which basically tells us exactly how you need to change the passive variables when the active variables change. So a point C of the manifold is specified by the relationship between the active variables and the passive variables on that surface, the manifold. The tangent space, this notation is kind of tricky here. The notation here is a little wrong. Let me fix it. It's the graph of the derivative, but should be written like this. So if you've used a graph to define a particular manifold, then the tangent space is the graph of the derivative. It is a k-dimensional subspace of Rn. If you used a locus function, that's our second option here of how we define a manifold. We now have f of z equals 0. That's our locus. That's how we described it. It maps from Rn to Rn minus k. The tangent space is going to be the kernel of a linear transformation. Remember, so long ago, and you're like, why is linear algebra coming back? But so long ago, we talked about kernels of linear transformation. So the kernel of df will be the basis for our tangent space. And very last, if we've used a parameterization to describe our manifold, well, in this case, any point of the manifold is the image of some point in the parameter space, and so the tangent space is going to be the image of d gamma. So remember the image, you can take a look at the columns of a matrix and know that that's the image. Well, the image of d gamma, when you compute that, that is going to be the basis for the tangent space for your manifold. What's interesting is that no matter how you have described it, as long as you compute it in the respective way, you're going to get the same answer about bases for the tangent space. That's one of the great things about this. In fact, that's a really important skill to have. You'll be tested about it on the homework. You'll be tested about it on, I'm sure, the final exam. It's sort of a notorious Paul question. Sorry, Paul, I'm giving away all your secrets, but to be able to compute a basis for the tangent space to a manifold in more than one way. What's important about it is that it contains these increment vectors that lead from C, a point that's actually on the manifold, to nearby points that are almost on the manifold. And there are some practical applications to this, which we'll get into in the next video.